All right. Well, trust you did well on that quiz 17. If you haven't taken quiz 17 yet, go ahead and take care of that. And then we'll get into this lesson. Page 200 in your textbooks. And I want to talk about, again, we've tried or at least I've tried all throughout this chapter to take you from what you know about motion from earlier chapters and then kind of relate to how it changes just a little bit here, dealing with rotation. For instance, there's a term that you should remember from the past, translational equilibrium. Translational equilibrium, if I can get it spelled correctly. Do you remember what translational equilibrium was? Dealing with a free body diagram, for instance?
It was at rest. Mm-hmm.
Okay, the body was either at rest or at least it wasn't...
In motion.
It could be moving technically, but it couldn't be accelerating. Translational equilibrium was accomplished when a body wasn't accelerating because what would cause a body not to accelerate?
Forces.
All the forces balanced out, right? All the forces cancel. So we said translational equilibrium, by way of review, is when the sum of all the forces is equal to zero, therefore acceleration is zero. For instance, if Michael was walking down the hall, and he was walking at a constant speed, all the forces would be in balance, right? Whatever, if he's not accelerating, then there's a consistent thing. And if somebody came up behind and started pushing Michael, but somebody also pushed Michael from the other side, and they perfectly balanced out, Michael would continue moving whatever rate he was. If something were slowly sliding down a ramp, but it was not accelerating, okay? Then that means that the frictional force and the weight, the frictional force resisting the descent and the weight in the x balance each other if it goes perfectly without accelerating. Unlikely, but possible. That's where all the forces cancel out. And the idea was to look at the x's, to look at the y's, get the y's to balance out, the x's to balance out and such. Now let's talk about rotational equilibrium. Rotational equilibrium. Okay. Rotational equilibrium. Well, rotational equilibrium, we're not concerned with forces all balancing out. We're concerned with torques all balancing out. So rotational equilibrium is the result of the sum of the torques equaling zero. So if all the torques on a body balance out, then we have rotational equilibrium. And if there is rotational equilibrium and all of the torques balance out, then it's not that we won't have acceleration, but we won't have angular acceleration. So if the sum of the torques equals zero, then angular acceleration equals zero. Same basic idea, but we're dealing with torques now. Remember with forces, I said that if a force acts this way and another force acts that way, they're in opposition to each other. They would be collinear, right, or anti-parallel, acting in opposite directions. We'd basically subtract them, right? With torques, it doesn't necessarily work that way. There are basically two categories of torques, two directions of torque. And since torque is rotation, we're going to name them very practically, directions you've used your whole life. There's clockwise, which is any torque rotating in this direction, and there is counterclockwise, which is any torque rotating in the opposite direction. So I assume are familiar with the terms clockwise and counterclockwise from pretty much your whole life. You've used those terms. Well, we're going to continue to use them. We don't have cooler scientific-y sounding terms, just clockwise torques and counterclockwise torques. And it's important to recognize that because there are times where torques may look like they're in opposite directions. Forces, for instance, could be in opposite directions, but the torques are in fact working together. Let's consider for a moment, let's suppose this is an aerial view of a very thin ruler on the very fat pencil tip, okay? So thin ruler, fat pencil tip. If a force was applied like this, and another force was applied like this, both of these would cause the object, the ruler, to rotate which direction? Well, it would push this side downward, but what direction would the whole body begin to rotate? The whole body would begin to rotate counterclockwise. So these are both counterclockwise torques. We would say that these are cooperative torques. They're working together. If I were to take a force here and a force here, well, technically, if you're just looking at forces, they're parallel. They're acting in the same direction. But This particular force, if applied, applies what type of torque? Counterclockwise again. This one, by putting it on the other side of the pivot, produces what direction of rotation? Clockwise. So these would be competing torques. If you looked at them as forces, you'd say they're, like I say, parallel forces. They're acting in the same direction. But as torques, they're acting opposite each other. Similarly, right, if we had a force acting here and a force acting there. Well, here's a counterclockwise torque, and here's a clockwise torque. Evidently competing, right? This would be like you on one side of the door and sibling on the other side of the door. And, but if you were to take that same basic approach and put a force here and a force here, notice both of them are producing that same counterclockwise rotation. So while here we would have competing torques, and here we'd have competing torques, here we would have cooperative torques in both cases. So when we deal with torques, it's important not just to look at the direction the arrow, in a sense, is functioning, but depending on where they're placed in respect to the pivot, is a torque clockwise or is it counterclockwise? Does that make sense? And ultimately what we will want to do to establish rotational equilibrium is we would want to say that the sum of all the clockwise torques balances out or equals the sum of all the counterclockwise torques. If that's true, then there will be no angular acceleration. Now, again, technically it is possible the body could already be in rotation. Multiple torques are applied, and if they all cancel out, then the body continues at its same consistent rate of speed because the torques all cancel. Generally, we think of it in the sense of the object is just sitting there, not spinning at all, and all the torques cancel, so it continues to not spin. By the way, not spinning completely we refer to as static equilibrium. Static equilibrium. And that is a situation with both translational and rotational equilibrium are applied, right? For instance, if I slide the book across the tabletop, right, sliding it, okay, it's not spinning. There is rotational equilibrium, I guess you could say, if I push it head on, but not translational equilibrium. On the other hand, if I were to push a corner, I could cause it perhaps to spin without necessarily moving anywhere else. So we could have translational equilibrium, but not rotational. Now it's got both, okay? So we tend to think of that as static equilibrium. Look at page 201, and you see a couple different examples, by the way, leading up to this, of different types of torques, competing torques versus cooperative torques. But look at figure 13.22 at the bottom of page 201. We see a whole bunch of torques all applied to the same body, right? And so the key here is to analyze each torque individually. Important to remember, torque is the product of two things, class. Force times radius, right? So we want to look not just at the force, but also the radius of the force. So looking at the very first, I'm just going to work my way left to right across the diagram here. The first force, class, is a force of 4 newtons. Now looking at with respect to the pivot point marked P. They kind of got it broken down funny, but do you see how from P going toward the left side, there's 0.3 meters to the first force, an additional 0.5 meters to the next force, and then an additional 0.2 meters to the next one. What is the total radius of the 4 Newton force? 1 meter. So what is the torque produced by the 4 Newton force? 4 Newton meters, right? 4 newtons times 1 meter is 4 Newton meters. What direction is that first torque? Okay, that first one is clockwise. So we'll say there are 4 clockwise Newton meters from the first torque that's applied. Look at the next force. It's a 2 Newton force. What's its radius? 0.8 meters. Okay, so what is the torque produced by that force?
1.6.
In which direction? Counterclockwise. So there's 1.6 Newton meters acting counterclockwise. That's from the second force, or the second torque. The next force we see is 6 newtons. Its radius is only 0.3, right? It's 0.3 from the pivot, right? Now again, the 2 newtons was 0.5 beyond the 6, which was 0.3. That's why its radius was 0.8. The very first force was 0.3, and then another 0.5, and then another 0.2, which added up to a total of 1. But the next one is just 0.3 meters from the pivot point. What is the torque produced by the next force? 6 times 0.3? You can use your calculator if you need to.
1.8.
1.8, right? Okay, so is that clockwise or counterclockwise? That's going to act clockwise, right? Going upward on this side of the pivot is going to carry it this direction. So put it in the clockwise category, 1.8 additional Newton meters. Go to the next force. It's on the other side of the pivot now, but it's an upward force of 10 newtons. The radius is 0.2. So what's the total torque? 2 Newton meters, right? 0.2 times 10. Which direction? Counterclockwise, right? It's carrying it the other direction. So 2 Newton meters going counterclockwise. Look at the next force. 8 newtons. What's its radius? 0.5 meters total, right? 0.2, then another 0.3, so 0.5 meters. So 0.5 meter radius, 8 Newton force. What's the torque? 4 Newton meters. 8 times a half is 4 Newton meters. What direction? Counterclockwise. By the way, if we wanted to, we say, hey, these two cancel. We wanted to save ourselves some work on the tail end. And then the final force is a 3 Newton force. What's its radius? 1 meter. So the torque then is 3 Newton meters. What direction? It's working clockwise. All right, so if I go ahead and cancel the 4 Newton meters from both of those, because they're opposite each other, they're canceling, it makes the math a little bit easier. What is the leftover clockwise torque? 4.8 Newton meters. What's the leftover counterclockwise torque? 3.6 Newton meters. So who wins, clockwise or counterclockwise? Again, imagine a large bar, a whole bunch of people pushing in different positions on the bar. The winner is the clockwise. The bar will move clockwise. What is the net torque? 1.2 Newton meters. That is the sum of the torques, or we could say the resultant torque. Just as if we took all the different forces that act on something, figure out what it all is when the dust settles and the smoke clears, same kind of thing with torques, but we have to categorize them either as clockwise or counterclockwise. Does that make sense? Questions? Yes, sir.
Your directions are the same for clockwise and counterclockwise.
I was wondering if anyone would notice that. Good job. Yeah, Kendall's been screaming at the screen. She's like, that's clockwise, that's clockwise, counterclockwise. I was just seeing if you were paying attention. Okay, I screwed up. All right, questions on this? All right, so how will we use this whole static equilibrium thing, rotational equilibrium thing? The idea that torques would cancel out if there's no rotation, or no additional rotation, I guess we could say. Turn over to page 202, and let's look at just one example problem. We have just a few minutes remaining. And let's take a look at example 13.12. And read that for us, if you would. Audrey?
A dumbbell is suspended on a cord with the length of a bar is 1.2 meters if the masses at the end are 20 kilograms and 10 kilograms. At what point on the bar should the cord be attached to hold the dumbbell stationary in a horizontal position? Assume the bar is weightless.
All right. Obviously, assuming the bar is weightless is ridiculous, but we'll go with it, okay? That's not going to be the case, and we'll account for the bar tomorrow when we have a little bit more time. But for now, we'll ignore the bar, as much of a stretch as that is. And normally, if you were to just pick up dumbbells, or a barbell, actually, it's not a dumbbell, it's a barbell. But if you were to pick up a barbell, so there's a couple errors. A weightless bar, and they call it a dumbbell when it's a barbell. Thoughts about Michael are cruel and unnecessary at this point. But anyway, the barbell, right? Normally, you'd pick up a barbell at the middle, right? You'd have hands on either side of what would be dead center. That's normally where you pick it up, because normally you'd have the same weight on both sides. Well, they didn't do this. This is very strange. They put 20 kilograms on one end of the bar and only 10 kilograms on the other end. So if you went to pick it up, like that, because the 20 kilograms would be weighing it down, correct? So if they're going to suspend it from a cord, they're going to have to slide the cord closer to where there's 20 kilograms. Does that make sense? That's just going to be necessary. And the question is, where must they attach it? Well, what we're going to draw is not a free body diagram, but sort of like a free body diagram, but our object will be literally a bar, just a line. And this line will represent where all the torques will be applied. Picture this for a moment. On one end, there is weight bearing down. The weight that is the result of that in 20 kilograms. On the other side, there is weight bearing down. The weight that results from having 10 kilograms on that side. Technically, you should have weight for the bar as well, but they're ignoring the weight of the bar. And there's only one force lifting up on all of this, and that is the cord, the cable, the rope, whatever they called it. But that's not going to be in the dead center. They're going to shift it somewhere over here, correct? Now we know this, that whatever force bears down has to be countered by a force upward. But they don't give us the force, they give us the mass, don't they? So 20 kilograms, what is the weight or the force of 20 kilograms? Multiply mass times gravity here. So on one end of the bar, we have 196 newtons. On the other end of the bar, we have 98 newtons. 10 kilograms, so 98 newtons, which means how much force has to lift up in order to suspend this bar? 294 newtons of force. Now what we've got is we've got translational equilibrium. The sum of the forces in the y is 0. But we also need rotational equilibrium. And for that, we need to characterize all of these forces now as torques. Torque is force times radius. And so we've got to pick a point to be the pivot point. This is step number 1 after drawing the picture. You've got to pick a pivot point, and here's my recommendations, 2 recommendations. Number 1, pick a pivot point where there is a known force. When you pick a pivot point, put the pivot point where there is a known force. That'll make your life easier, as you're going to see here in just a moment. Also, I recommend you put the pivot point at one end of the object. It just makes your life easier. The book doesn't do this, which is a bummer. The book puts the pivot point where it would actually pivot, and that's at the cord. But that which is intuitive is not always easiest, right? And I'm lazy, so I have found if you'll put the pivot point at one end or the other, you're better off. So what I'm going to do is I'm going to make this end my pivot point. Any point could be, but I'm going to put it at one end, and I'm going to put it where there is a known force. Vantage number 1 of this. If this is my pivot point, what is the radius of this force? 0. Its distance from the pivot is 0 meters. Wonderful. That's fantastic. The other benefit of putting it at one end is since they told us that the bar is how long? Then I know the radius of the other force that's at the other end has to be 1.2 meters. It makes it easier to name the distances, the radii, if you have it at one end because you're accounting for the length. Now, what I don't know is where to put the cord, meaning I don't know its radius. So just call its radius x. Now, if this is the pivot point, stay with me, this torque is nothing. There is no torque right here. What direction would this force act if this were the pivot point? This would be acting counterclockwise. What direction would this torque act if this is the pivot?
Clockwise.
This would be going clockwise. And we know this, that if the bar were to hang perfectly level, no rotation at all, that the clockwise torques and counterclockwise torques would have to cancel. They'd have to balance out. They'd have to be equal. So therefore, 294x, force times radius, has to equal 98 times 1.2 force times radius. At your seats, solve for x. And what do you get when you solve here? Class? 0.4 meters. That means it's a 1.2 meter long bar, remember. We need to come over 0.4 meters from the heavy side. That's where we'll attach it. So the question is, where should the cord be attached? 0.4 meters from the 20 kilogram end. You could, I suppose, say 0.8 meters from the 10 kilogram end. That's not particularly intuitive. Or, remember, halfway would be 0.6 on both sides. You could say 0.2 meters from the center on the 20. There's a number of ways you could express it, but the easy way, I think, is 0.4 meters from the 20 kilogram end. Okay, questions on that? Homework for this evening is to read over pages 200 to 203. Read over pages 200 to 203. Again, you'll be looking at some example problems of these. Study over those again. This is the second time I've given you these pages to read over. This time I want you to answer some questions on page 204, questions 24 to 27. Page 204, questions 24 to 27. Kendall, praying for you and your family, and hoping to see you back here very soon. All right, have a wonderful day. You are dismissed.